So does this show you the open spot on your side?
I haven't checked. Let me see. I know we have 38 spots in the course, but it looks like there's 38 enrolled. Yeah, it looks like I have one spot.
Yeah.
Yeah, I don't know.
Oh.
That's all I see, so that's why.
That's so weird.
Yeah. So records and registration, they told you just wait.
Wait.
Okay, I would follow up with them
Yeah.
one more time and see. Um, there's I don't know. There's nothing I can do on my end from
Yeah.
here. So yeah. All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Staying dry, hopefully. It's a lot of rain out of nowhere. Apparently it's supposed to get really bad this Sunday and next Monday, so make sure you guys are taking care of yourself. Drive carefully. I think I saw 3 car accidents on the way to work today, so yeah, definitely could be it's dangerous driving out there. Okay, so the plan for today is we're just going to continue with our lecture notes. I think we left off last time with uniform series. So I got a couple of examples talking about that. After that, we have one more type of cash flow to go over, which is called the arithmetic gradient. So we'll introduce that, do a couple of examples, and then we'll kind of wrap up this section before we get on to present worth analysis for next week. Okay. A couple of announcements. If you haven't sent me, I think the majority of the class have already done this, but if you haven't sent me your introductory email, please make sure to do that. The due date for that is tomorrow, so you want to make sure you get that in so I can give you credit for it. And the first actual problem set is posted as well, so you definitely want to get started on that as well. You should be able to do the vast majority of it. After today, you should be able to finish up just whatever's left from that. Okay. All right. Any questions I can answer before we get started for today? Okay, all right, let's go and get started. Okay, and so we're on this kind of this first big chapter here about equivalents, interest rates, cash flows, kind of introducing a lot of the concepts that we'll be kind of revisiting a lot throughout this entire economics section. Okay. And so in particular, on Tuesday, we left off with this concept called the uniform series. Okay. And so just to kind of refresh your memory, a uniform series is your kind of your basic recurring type cash flow. Okay. And what sets the uniform series apart, or what makes it unique, is that it's uniform, and that it has the same amount of cash flow or the same amount of money that's occurring at every time interval. Okay. Okay. So visually, if we were to look at this from a cash flow diagram perspective, right? A uniform series would look something like this. So let's say we're going to look at a uniform benefit. Okay, we can use a uniform series to describe a benefit and a cost, and they're kind of different. They're mathematically we treat them the same, except just with the negative sign. So here I'll draw a uniform benefit. Okay. So each of these arrows have the exact same amount. Okay. For A here defines the amount of uniform series payments. That's the amount that you're, in this case, the amount of money that you're earning at each time period. Okay. And so the last thing that we did on Tuesday was that we have this definition here, which is good, but a lot of times when we do economic analysis, we need to convert this uniform series to a different type of cash flow just so that we can compare, right? Remember, a big part of our discussion on Tuesday was this concept of equivalence, where you can only really add money together, add, subtract, do any kind of mathematical operations if the money is being all put in the same time period. Okay. And so that's especially important with uniform series, because if you have a recurring payment, right, you want to make sure you convert it all into a single lump sum, so that you can perform calculations on that. Okay. And so the last thing we did was we derived a formula for converting a uniform series to a future sum. And I'm sorry, I don't have a better name for this formula. That's literally what it's called. Okay. And so we said our formula here was F is equal to A times quantity 1 plus I raised to the n power minus 1, all divided by I. Okay. And so in this formula here, if we know everything on the right-hand side, so let's say that we know our uniform series amount, we plugged it in for A. We know our interest rate, I. Remember, interest rate is always expressed as a decimal. And the last variable we need is N. Okay. Then we can use this formula to convert that uniform series to an equivalent future sum. Okay. All right. And just because it'll be relevant for something that we talk about maybe halfway through the class, let me kind of show you what this looks like visually as well. Okay. Okay. So when you convert between different cash flows, you're I think a really nice way to visualize it is through their cash flow diagrams. Okay. Okay, so let's say that we have a uniform series amount. So let's give it a uniform benefit again. Okay. So everything here is uniform, so it all has a value of A on every arrow. Okay. By using this formula, we can convert this. And so we can say that, we have this uniform series amount for five, in this case, for five time periods, we're going to be gaining a uniform series amount of A. Okay. If we want to find out how that's equivalent to something in the future, okay, we would use this formula. And so by converting it into a single lump sum, an F in this case, right, it would be something like that. Okay. So by applying this formula here, we're converting that uniform series, a recurring recurring revenue here that occurs for 5 years in a row. Okay. And we're finding out what that's equivalent to at the end of the 5 years. Okay. Because remember, when you have interest rates, when you have different time periods acting up, right, you can't simply just add the 5 things, right? So it's kind of a tempting thing to do is, if you were to total up the amount of value or the amount of money you would have at the end of the 5 years, right? One thing that's tempting to do is just A plus A plus A plus A plus A, right? You simply just add that up. But you can't do that because each of those A's occur at a different time. Okay. And so in order to kind of properly do this conversion, to kind of get the equivalent sum at the end, you need to apply this formula with the interest rates in there as well. Okay. Okay. And so now that kind of begs the question of, do we have another formula also for different conversions? And we do. All right. So that's the F to A conversion, or I should say A to F conversion. We also have an A to P conversion. Okay. Which I have this other page. Okay. So I'm going to skip the derivation for this just because, we already did one derivation last time. But if we wanted to convert a uniform series to a present sum, we'd use this formula. So we have P is equal to A times 1 plus I to the n minus 1, all divided by I times 1 plus I to the n. Okay. And so let me visualize this for you just so you can see it. Okay. So just like above, we're going to start with the uniform series amount. Each of these have a value of A. And then by plugging that A into this formula, we get the equivalent amount, but not in the future, but in the present day. Right. Right. So these conversions are going to be really key, and ultimately, all the formulas that I'm going to introduce to you guys, we're about halfway done with the formulas in this section. All of them kind of serve the same purpose of being a conversion factor between different types of cash flows. Okay. So what you'll notice for a lot of the for this homework, for this problem set that's out there right now, I'm asking you guys to draw the cash flow diagram along with doing the analysis, right? Of course, once you get better at these problems, once you start to get the intuition for them, you can start to do these conversions without the visual guide. But I think when you're first starting out, especially if the concepts of interest rates and equivalents are new to you, I would definitely recommend drawing out the cash flow diagrams for each of these problems, just so it's kind of easier to kind of see what's going on. Especially for more complicated problems where you have to do multiple conversions in a single step. And so we'll go over that as well. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So let's do an example. Okay. So in this example, let's say that we have a couple of your friends. They just got married and they want to save up for a new car. Okay. So they don't have the money now, but they're planning on putting money away into a high yield savings account, maybe a CD, or maybe put in the stock market, okay, to save for that car. Okay. So they make an initial deposit of $5,000. Okay?
Hey,
And
Professor.
then each year after that, they can add $7,500 to this account. All right. So let's say that this account has a interest rate of 8.3%. They want to compute how much money they'll have in the account after 2 years. Questions from the chat. So the previous formula for P is converting a uniform series to a present amount. That's correct. Yes. Yeah. Yeah. So the way to kind of read these equations is whatever's on the right side, you'll see some symbol there, either a P or an A, an F, and later on we'll introduce G as well. And so that's the thing you're converting from. And then the thing on the left-hand side is what you're converting to. And so in that case, the P is on the left-hand side of the sign. That's what you're converting to. The A is on the right-hand side. That's what you're converting from. Yeah. Okay. So if this account has an interest rate of 8.3%, how much will be in the account after 2 years? Okay. All right, and so with this, we're starting to get into little different types of word problems here. So as always, a good thing to do whenever you have a word problem of any kind is to circle all the relevant information. So let's circle all the cash first. Okay. And so first here we see that we make an initial deposit of $5,000. Okay. So we know that $5,000. That's our initial deposit. So this is something that's present in year 0 or time period 0. So this is a present sum. That's money that the couple has on hand right now, right? So we can call that a P. Okay? Bless you. And then what the problem tells us is that this couple can deposit $7,500 each year into account after this, into the account after this. So of course, the operative keyword here is per year. And so this is a recurring type of payment or recurring deposit. Okay. So this is a uniform series. Because it's a recurring payment. Okay. Or uniform series is A. Okay. Next, we have the interest rate. So let's go ahead and convert that to decimal form. So 0.083. Okay. We have the time period N, and here is 2 years. Okay. Okay. And then the last thing that we'll highlight here is well, there's nothing really to highlight, but it's it's looking at the problem and thinking about what is it asking for from this problem. Okay. So the last sentence here, how much will be in the account after 2 years, right? This problem is asking for an amount of money that's going to be there in the future. Okay. Okay. And so from that last statement, it's asking us for that future sum. Okay. And so in other words, it wants us to compute F. Okay. Which means that we're going to take our cash flows here, our two cash flows, and use formulas to convert them to a future sum. Okay. All right, so we have two types of cash flows here. We have a present sum, so we know how to compute that. We can use our compound interest formula. And then we're going to use one of the two equations that we just went over to convert that uniform series to a future sum as well. Okay. All right, any questions on the just on the setup for the problem? Okay, all right, so let's go ahead and get to it. All right, so we'll do these one at a time. And so we we don't have to convert everything at once. Okay. Remember, once you convert everything to the same type of cash flow, or basically a cash flow that occurs at the same time, you can just simply add them. Okay. So if we convert that present sum to a future sum, and then we convert that uniform series to a future sum, we can take both of those results and just simply add them together. Okay. So let's start with the $5,000. So this $5,000 we want to convert from P to F. Okay. Let me switch from the paper is annoying me, so let's switch back. Okay. So our formula for this okay, this was our compound interest formula. Now that we have kind of a different context of this, you can kind of tell what this is converting to, right? So on the right-hand side of the equal sign, we have a P. On the left-hand side, we have an F. So this tells us that this formula here converts a P to an F. All right, so we have all the information here, so we can go ahead and plug it in. Our P in this case is 5,000. Our interest rate is 0.083. Okay. And our N here is 2. Okay. And so we plug in for all of those, we punch it into a calculator or MATLAB or whatever you use to compute things nowadays. Okay, we get $5,864.45. Okay, good. All right, and so our second step here is to convert that 7,500, that's an A, to an F. We want to convert from A to F. Okay, and so we're going to use our formula, and so we have F is equal to A times 1 plus I raised to the n minus 1 all divided by I. Okay. We have everything in this equation here. So we have 7,500 for A multiplied by 1.083 squared minus 1 all divided by 0.08. All right. And so we do the math for this. We punch into a calculator. We get 15,622 and 50 cents. Okay. So now that we've converted both of these to F's, we can simply add them together, okay? Because these are now both cash flows that are occurring at the same time, okay? They're both in the future in 2 years. Okay. And so if we add them together, we get 21,486 and 95 cents. Those are here, total amount in account. After the 2 years. Okay. All right, any questions on that example there? All right, and so that's kind of the basics of these cash flow conversions. Okay, so we have our 3 formulas now. You can invert these formulas, and so sometimes it happens where you're given a so let's say you're given a present sum and you want to compute the uniform series. Okay. Okay. All right, so let me give you an example. So we have F is equal to A. So I'm just rewriting the formula that we had up there. So we have F is equal to A times 1 plus I to the n minus 1, all divided by I. So what you can do from here, so let's say that you want to convert an F to an A, right? Okay. We can use this exact same expression here. We just, take everything else and move it to the other side of the equal sign. Okay. All right. And so if we do that, I'm going to multiply this entire thing by the inverse of this. Okay. Okay. So I'm going to multiply by I divided by 1 plus I to the n minus 1. Okay. And so we get A is equal to F times I divided by 1 plus I to the n minus 1. So once we get to the arithmetic rating, I'm probably only going to show you the formula in one direction, but just know that you can use that same formula to go in the opposite direction too. You just kind of switch the order of the terms. Okay. All right, and so we can do the same thing for the present sum and uniform series. And so the other kind of the other equation with P, as we get A is equal to P times quantity I times 1 plus I to the n divided by 1 plus I to the n minus 1. All right, so these conversions just go the other way. So if you're given a P and you need to compute an A, or if you're given F and you need to compute an A, this is how you would do. Okay. That second formula in particular is very useful because if you're borrowing money from someone, usually you're going to pay that back in a uniform series payment, either per month or per week or per year or whatever. Okay. So that second formula there is useful to compute, how much money you would pay, each time period. All right, so I have a very quick example for that one. Okay, so let's say that you borrowed $800 from your uncle to buy a new phone. And so he expects you to pay him back in a uniform series of payments over the course of a year. So each month you're going to pay him an amount, and then by the end of the year you'll have paid it back. Okay. Right, and of course, your uncle's always looking for ways to make money, especially off his nephew. And so he's like, I'm going to charge you 5% interest on this on these payments. What kind of uncle makes money off their nephew? This is based on a past experience, by the way. I wish I knew how to do these calculations back then. I could have verified whether he was ripping me off or not. Okay, so you want to compute. Okay, your uncle says that you owe him about $90 each month, but you want to verify that this is actually an amount. So you want to compute. You want to compute your monthly payment amount. Okay. So this is a situation where you want to compute your uniform series amount, but you're given a different type of cash flow. Okay. And so the only cash flow we really have to identify here, this is just a one conversion problem, is the $800. Okay. You're using that $800 to purchase the phone today. So this right here is $800 is a P. Okay. So we want to convert this $800 P into an A, basically. Okay. All right, so we're going to use the formula that's just right above it. It's kind of very nicely framed here. Okay. So we're A here, we're going to plug into this formula here. Okay. So from this formula, we have A is equal to P, which is 800 multiplied by quantity I. I in this case is 0.05, 5%, okay, times 1 plus I to the n. So it's going to be 1.05 raised to the 12th power. Okay. And then all divided by 1.05 to the 12th minus 1. Okay, so that'll tell you how much you're going to owe your uncle each month. Okay. All right, so you punch all this into a calculator, and what you get is $90.26. Your uncle was telling the truth, so you owe him about $90. All right, any questions on this example here? Okay. Speaking of this is completely unrelated, but I've realized recently that that there's kind of like an iPhone like supremacy thing like kind of going on. I had no idea this was a thing until all my friends started bullying me for having a Samsung phone. Is that a thing? Like, do you guys bully your friends if they don't have iPhones?
Nice.
You do?
Text bubbles are green.
I bully my friend for having an iPhone.
Okay, good. So I have to go, but let's just not bully anybody. Everyone just has a phone that they want. But it's mostly the green text bubbles. Because whenever we have group chat and it turns to me, it's like, oh, it's always fucking Justin that has the green text bubble. I didn't know it was a thing. Yeah. And then my friend is like, my friend was like, oh, my little cousins in high school are doing it. So now I'm bullying my friends for not having iPhones too. I was like, you guys are mean. Okay. All right, back to the scheduled programming. Okay, so now that we've covered uniform series, right? We have kind of a nice collection of formulas kind of under our belt. We know how to convert between all of these. Okay. There are some limitations in terms of how you can perform those conversions, though. Okay. Sometimes the conversions are not going to be as straightforward as just doing one step. And so our next section, before we go over the last cash flow type, is going to be cash flows that do not meet, or cash flow conversions that are not standard form. Okay. So what do I mean by standard form, right? Every type of cash flow has kind of an implied standard form. We've been using it up in this point. I just haven't really drawn too much attention to it. And the standard form is it's not that the cash flow itself has a standard form by itself, but it's a standard form when you connect it to the amount of time periods. Okay. Let me give you the most obvious example. Uniform series. Okay. So the uniform series that we just finished covering, we know that it's a recurring payment, a recurring cash flow that occurs at every time period, right? You need to know how many time periods that's going to occur. Because there's a difference, right? And so, when we compute a uniform series, all we compute is just A. Okay? The A tells you how much cash flow is going to be occurring at each time period, but it doesn't tell you how many periods it's going to occur. I don't think recurs is a word. Let me put repeats. Okay. So there's a difference. And so if you have an A of, let's say, a positive 100, right? There's a difference of this repeating 2 times. Right? Versus it repeating 12 times. I only drew 10 dots. And so the thing with the uniform series, and so a uniform series typically does not stop early. And so when you're given a uniform series as well as a time period, the assumption is that that uniform series will keep recurring or keep repeating up until the very end. Okay. So that's the standard form for a uniform series. Okay. The other thing for a uniform series that makes it standard form is that the first payment or the first time it repeats is in year one. Okay. If you have a uniform series that doesn't start in year one, so let's say it starts in year 3 or year 4, right? Even year 2, that is a non-standard uniform series, and we'll learn how to deal with that in a bit. Okay. But this is important to know. Okay. All right, uniform series is probably also the most complicated one. The other one that has kind of a somewhat tricky standard form is the future sum. Right. Similar to the uniform series, right? When you pair a future sum with the time period, right? The future sum is always assumed to occur at that time period that you specify with the number. All right, so just as a quick example, let's say that we have two future sums here, right? They may have the same cash amount, right? Let's say we have one future sum occurring at year 2, another future sum occurring at year 4. Okay. So this one right here, they may have the same F value, but this one right here has an N value of 2, and this one right here has an N value of 4. Okay. It seems obvious, but once we start doing these kind of non-standard conversions, it's kind of important to kind of keep these in mind. Okay. Present sum is pretty easy to determine. Present sum always occurs at year 0, and so that's the standard form for that. Okay. Okay. So why are we talking about this? And so sometimes you're going to come across problems that have these non-standard type of cash flows. Okay? When you have these non-standard cash flows in a problem or a situation, oftentimes you need to perform more than one conversion in order to get it to a standard form or a form that's convenient. the reason for this is that when you perform a conversion, and you can look back at the formulas that we've talked about so far, right? In every single formula that we've been using, we assume that the end value is the same between the two things we're converting between. Okay. If that doesn't make sense yet, then we're going to do a couple of examples to kind of illustrate with that. Okay. All right. These non-standard conversions are probably the trickiest part of this first unit, just because you're kind of at this point still where you're kind of still building intuition, you're still getting used to the standard forms. Sometimes it kind of seems like a puzzle almost to get the cash flows into the form that you need. Okay. So definitely take your time with these problems. I didn't assign any of these to you in the first homework set, but these will be part of the second homework set. So definitely do these slowly and kind of visualize every step. So draw your cash flow diagram so that it helps tremendously. Okay. All right, any questions on this before we jump into an example? Okay. Okay, so with this example, I'm just going to do it visually, okay? And so I'm just going to draw the cash flow diagram. Okay. So let's say we have a five, in this case, these periods represent years. And so we have a 5-year time horizon. Let's say that we have a recurring benefit that occurs during the first 3 years only. So during these first 3 years, let's say that we get a benefit of $1,000 per year. Okay. What we're interested in is let's say that in year 5, so 2 years after the payments stop, you need to pay this back. So let's say that you're in a situation where you're borrowing $1,000 per year, and then there's 2 years of no payments. You don't have to make payments, but at the end of the 5 years, you have to pay 1 lump sum. Okay. Right. And so our question in this case is, how much do we have to pay back at year 5? Okay. So let's say we need an interest rate here too. So let's say the interest rate is 15%. Okay. So when you first look at this problem, this looks like a pretty standard kind of cash flow conversion type problem. We have a uniform series, okay, and we want to convert it to a future sum, right? And so you might look at this, and say, oh yeah, we have a formula for this, right? We have an A to F formula. Okay. And so that formula for that is F is equal to A times quantity, 1 plus I to the N minus 1 divided by I. Okay. We have everything in this, in this problem here. Okay. So we have the A amount, right? The uniform series amount is 1,000. We have the interest rate. We have the interest rate is 15%. So that quantity there is going to be 1.15. Okay. We see from the diagram here that the payment occurs 3 times. So our n here is going to be 3. Okay. And then we're going to divide by the interest rate, which is 0.1. All right, so we'll punch these into a calculator. And what we get is $3,472. Okay. Okay. So you may look at that and you say, like, that's our answer, right? So we did what the problem asked us to do. We took our uniform series and we converted it to a future sum. Okay. And of course, with all that foreshadowing, obviously this is not the answer we're looking for. Okay. Because remember, when we perform this conversion, okay, when we apply this formula here, okay, the assumption is always that the n is fixed. Okay. Okay. So we chose n is equal to 3 because the uniform series repeated itself 3 times. Okay. That makes sense, right? We only had 3 payments, and so our n should be 3 here. But that n is also going to apply to the f that we converted to. Okay. And so this $3,472, this is a future sum, okay? But it's a future sum not at year 5, it's going to be at year 3. Okay. And so all we've done is this. And so let me go ahead and draw the cash flow diagram one more time. Okay. All right, so we've taken that $1,000 per month or per year payment, okay? And we've converted to a single sum right here. Okay. And so that amount is 3,472. Okay. But that's not the future sum that we're looking for. We're looking for the future sum in year 5. Okay. And so we're going to need to do one more conversion here. So we need to convert this F in year 3 into year 5. Okay. Okay. And in fact, now that we have it in this form, we can go ahead and kind of redraw this to make it a little bit easier to see. So, everything that occurred before this, the 0, 1, 2, doesn't matter anymore. So we can kind of redraw our cash flow diagram to look like this. We have our F 3,472. Okay. And this is the one that we want. So we'll call this F5. Okay. And we can renumber it too. So so from this diagram here, you can see we're from our current point at year 3, we're only going 2 years into the future. Okay. All right. And so the nice thing here is that these are just single sums of money. Okay. And so we can just use our compound interest formula. And so we have F is equal to P times 1 plus I to the n, where P here is 3,472. Okay. And since we're only going 2 years into the future from here, this n is equal to 2. Okay. All right, so we plug those in and we get $4,590. All right, so that's the final answer for this one. Okay. All right, so you want to be careful of these non-standard conversion problems. And so, for this problem, it really helped to kind of draw it out. Okay. And so make sure you're using your cash flow diagrams to help you out with these ones. Okay. Question. So if I knew the value of F was going to be positive, why did I draw it pointing down? Yeah, it's a good question. I kind of just so this problem did have text. I just kind of skipped it just for the sake of time. But kind of the context for this problem was that you were borrowing money $1,000 per year, and you're paying it back. And so that this F amount is almost like a payment for you. So it's something that that's leaving you. But I kept the diagrams the same, but I forgot the flavor text. So yeah, that 5,590, it should be negative because that's money that you're paying. But it's just kind of a wording of the problem thing. Yeah. All right. Any questions on this here? Okay. All right. I'm going to do one more example with this, just because this part is kind of tricky. This one's a little bit more complicated. I don't have numbers for this one, just because this is an example that's not in the notes. But I want to kind of walk you through it visually to kind of see what this is. Okay. All right. So let's say that we have a cash flow diagram like this. Okay. And let's say that we have a situation where, we are receiving payments every 2 years. Okay. And these are all in different amounts. Okay. So this would be F1, F2, F3. Okay. So let's take this example and let's convert it to an equivalent uniform series. And so let's convert, the uniform series, just one A value that encapsulates, that's equivalent to these 3 payments. Okay. And I guess I should add too that this uniform series will be, across all 6 years. And so we want to compute an equivalent uniform series where n is equal to 6. Okay. All right. So a little bit more involved in this time, but the reason I want to bring up this example here is that, usually there's actually more than one way to do a non-standard conversion. Okay. And so you can go through different paths, right? In the end, you're going to get the same answer as long as your logic is sound. Okay. I just want to kind of show you that there's different ways to do this. All right. So let's do each of these one at a time. So F1, F2, F3, right? Let's convert each of them individually to an equivalent A value, and then we'll add them all up at the end. Okay. So let's go from the right, actually. So let's start from the right and then go down. So let's start with F3. All right, so F3 here, this is actually our only standard conversion. So because we have F3 here, or it's already occurring at year 6. Okay. And so to convert it to a uniform series with n is equal to 6, we only need to do one conversion. Okay. All right, and so for this, we're going to use our inverse formulas. We have A is equal to F, in this case, F3. I didn't give you an interest rate in this time just because, we're doing everything for symbols. I'm just kind of showing you the logic of the conversions. Okay. All right, so this will be A is equal to F3 times quantity I divided by 1 plus I to the N minus 1. Okay. All right, so that's good. All right, so now let's come to F2. So F2 is a future sum in year 4. Okay. And so we want to convert it to a uniform series over 6 years. And so this is a non-standard conversion. Okay, so let's kind of strategize first before we kind of jump into it. Okay. All right, so one way to do this is we can first convert this F2 into year 6. Okay. And so we can use our compound interest formula. We basically just convert this amount 2 years into the future. Okay. And then from there, once it's a future sum in year 6, we can use the exact same formula that we had above. Okay. Okay. All right, so let's do that. So let's say it's getting a little confusing here with the numbers, but I'll call this F26. And so this is our F2 value converted to year 6. Okay. And so to go from year 4 to year 6 is just 2 years in the future. So we're going to have F2 multiplied by 1 plus I squared. Okay. Well, I guess in this formula up here, we can plug in for n so that we know the n is 6 in this case. Okay. So I just changed this this number here to a 6. Okay. Right. Okay, so now that this quantity here that I'm circling, now that this quantity is in year 6, we can then just convert it using the formula above. Okay, okay, so this will be A2. Okay. Let's plug in for F. And so instead of just a single number F3, we're going to plug in F2 times 1 plus I squared. Okay. So remember, this quantity is taking the place of that F in year 6. And then we're going to multiply by the same quantity over there. So we're going to multiply by I divided by 1 plus I to the 6th power minus 1. All right, so this is a 2-step conversion. So we moved a future sum to the far future, and then we distributed that through an A conversion. All right, any questions on that so far? Okay. All right, so finally we have F1. Okay, so F1 is a future sum in year 2. Okay. And so we want to convert this into a uniform series across 6 years. Okay. So for F1, we can do the exact same thing we did for F2. So we can convert it, we can push it into the future, convert it to a future sum in year 6, and then convert that to an A. Okay. That's totally fine. You can definitely do that. And of course, the only difference here is that, for the first conversion, since we're going from year 2 to year 6, that would be, you'd have that first conversion raised to the fourth power, because that's 4 years into the future, okay? So that's perfectly valid. That's you can definitely do that. You'll get the right answer, but no problem. Okay. I'm going to show you a different path. So let's convert F1 into a present sum. Okay. And then that present sum, we can then convert it to a uniform series across 6 years through a P to A conversion. Okay. So a slightly different path, but this is going to give us the exact same answer. Okay. Okay. So first is to convert it to a present sum. Right? So we're going to use an F to P conversion. So we have a P1 here is equal to F1. Okay. So this is the inverse of our compound interest formula. And so instead of multiplying by 1 plus I to the n, we're going to divide by 1 plus I. N in this case is 2. Okay. So we're taking that future sum in year 2, bringing it back to the past 2 years. Okay. This brings and I should be doing this for you. I should have done this for the last step, but let me visualize this for you. Okay. And so we started with this F2, right? Through this conversion here, we're going to bring this back into the past. And so it's going to convert it to something like this. I'm sorry, this is F1 and P1. All right, so F1 is occurring in year 2, and then by computing this conversion right here, P1 is equal to F1 divided by 1 plus I to the n. We're putting it back in the past by 2 years. Okay. All right. So now we can take this and we can go use our P to A conversion. Okay. But now we're going to convert this to A. Okay. And we'd still be in standard form here because present sums, by definition, as long as you have a single lump sum of cash in year 0, that counts as a present sum, and that's always standard form. Okay. And so we can take this present sum and distribute it across a uniform series through whatever amount of years. Okay. Okay. And so finally we have A1 here is equal to P1 multiplied by I 1 plus I to the n divided by 1 plus I to the n minus 1. Okay. Let's plug in for all the values here. So we have F1 divided by 1 plus I to the n. This should be squared. Okay. So I just plug in for P1. So P1 is F1 divided by 1 plus I squared. Okay. And then we're going to multiply by I times 1 plus I. Okay. Be careful here because you're doing multiple n's here because this conversion is for a uniform series for 6 years. Okay. So this n is going to be 6 actually. Okay. And then divide by 1 plus I 6th power minus 1.
Professor.
So you can simplify this a little bit. You can see that you have 1 plus I square on the bottom, 1 plus I to the 6th power on top. So you can cancel those and you get 1 plus I to the 4th power on top. You can do that, but you know, it's just kind of it's just simplifying an algebra at this point. Okay. All right, and so now that we have A1, we have A2, we have A3, right? We just simply have to add all these together and we get the equivalent uniform series for this cash flow. Okay. All right, any questions on this example here?
Yeah, which one is that derived from?
This one right here?
Yeah.
Um,
No, the one that's boxed in.
so this formula here, that's everything in this square brackets is the same as the square brackets. I just plug in for n is equal to 6. And then for P1, I plugged in this formula for P1 that we had up here. Yeah. All right, question. So since there are different n values, do you have a recommended way of noting the n in the formula? Yeah, it definitely gets confusing. And so the advice for that is actually to kind of sit tight, because there's we're doing these problems with the formulas, which you can do for the whole class if you want, but there's actually an easier way to using the formulas, and that's going to be to use the compound interest tables. And so I was hoping to get there today, but I don't think we're going to get there. So we'll probably talk about that on Tuesday. So the compound interest tables actually make these conversions a lot more convenient to do. Granted that your interest rate is an integer, but yeah, we'll discuss it then. So the advice for that is just kind of sit tight, tune in next time for okay. All right, so last thing I wanted to go over today, again, I think we'll probably just start it. I don't think we'll have time for an example. Is to talk about our last type of cash flow. And so that cash flow type is called an arithmetic gradient. Okay, so arithmetic gradient has the symbol G. Okay. All right, so just like the uniform series, the arithmetic gradient is a recurring type of cash flow. The difference here is that the amount that's going to recur is going to change, right? So a uniform series is a recurring cash flow where it all kind of stays the same. An arithmetic gradient is going to change. And the way that it's going to change is that it's going to increase over time. Okay. So visually, it looks like this. All right, and so standard form for the arithmetic gradient actually doesn't start until year 2. So I'll start here, there, that. Okay, so it looks like a data signal, right? All right, and so you can see that the amount of cash flow that's occurring in each time period is changing. Okay, and so the thing with the arithmetic gradient is that the amount of increase is the same between period to period. Okay, and so the amount that the cash flow increases this period relative to last period, that amount is the same, and that amount is given by G. And so if I were to label the amounts of increase here for or the amount of cash flow in each time period here, okay. Time period 1 has nothing, so time period 1 would be 0 times G. Okay. Time period 2 would just be an amount G. Time period amount 3 would be 2G, 3G, 4G, 5G, 6G, and 7G, just because I drew this with 8 for some reason. Okay. All right, and so if you look at it, you know, there's an increase of G as you go from one time period to the next. Okay. And so just like our uniform series and just like our future sums and present sums, we have formulas that we can use to convert an arithmetic gradient to our different cash flows. Okay. All right, so I'll give you 3 formulas here, but just know that you can invert them. You can kind of convert them depending on what you need from the formula. Okay. All right, so first we have our F and G formula. We have F is equal to G, okay, divided by I, multiplied by 1 plus I to the N minus 1 divided by I minus N. Okay. So this is the formula that you would use to convert an arithmetic gradient to a future sum. Okay, so this is G to F. You can also use this formula to convert from F to G. You just move all the I's and N terms to the other side of the equation. Okay. All right, so we also have P and G. So you have P is equal to G multiplied by quantity, 1 plus I to the N minus I times N minus 1. Okay. All divided by I squared, 1 plus I, the N power. Okay. So this is a formula that relates present sums and arithmetic gradients. Okay. And then finally, we need our equation for A and G as well. Okay. So we have A is equal to G multiplied by quantity 1 plus I to the N minus I N minus 1 divided by I 1 plus I the N. All right, so these 3 formulas here can be used to convert between G and the other cash flow types. Okay. And so if you ever need to convert these types of problems, you know, you would use these formulas. Okay. The reason I'm giving these to you in this form is because oftentimes the gradient is a little bit hard to visualize. So whenever you have a gradient, almost always you're going to want to convert it to another type, just so it's kind of a little bit easier to work with. Okay. But of course, if you do need to compute the gradient, you can kind of go the opposite direction as well, using these same formulas. Okay. All right. Any final questions on this before we wrap it up for the week? Okay. All right. So I'll leave it here for today. When we come back on Tuesday, I'll do a couple of examples with arithmetic gradients. There's a couple interesting wrinkles, especially with non-standard capital type problems with gradients, and so I want to make sure I cover that. We'll also cover the compound interest tables, and you'll when I do that, you're going to hate me for giving you all these formulas to begin with, but it'll be fun. And then we'll actually get into doing some economic comparisons next week. Okay. All right, so thank you guys for coming this week. I hope you guys enjoy the rest of your day. Hope you guys enjoy your weekend. Stay dry, and I will see you guys next week. Thanks, Brayden.
I think I signed up for like one month first, so it's pretty. Challenging. Do the recycle. Yeah. I might not have one. I think like you. Okay. So, yeah, there's lots of. No, I still don't know how to take this really. But later in the day, maybe just like one day or more, like, I guess like a slide. I got one, 4 to 5.